get the pulses, and when you use the pulses for your switching mechanism, you achieve the output voltage as you are seeing on the screen. Earlier, you have a square wave output voltage. In this case, what happened? We have series of pulses in the first half cycle and in the negative half cycle as you are seeing on the screen. But if you see the total harmonic distortion, you can find out the fundamental component like this, and we have the harmonics of very lower side. Because in a simple answer, as you know, for suppose, okay, fine, we will go with just now to understand this is the fundamental component and this is the fundamental current that appears when you give this voltage to an inductive loop. If you give this output voltage, a predominant voltage, to the inductive load, the current that is drawn from the inverter will be sinusoidal as you are seeing on the screen. Because the inverter, when it is drawing the current, it draws the current based on LDA by dt. This is the voltage drawn. So what happens? When the voltage itself is in this condition, the current that is drawn by the inductor will be sinusoidal. So basically what happens? Your fundamental voltage and your fundamental current drawn by the inductor is going to be sinusoidal with unity power factor. And on the other side, if you see the harmonic contents, the harmonic contents is fundamental component is here. That means, for example, if you consider a square wave, in a general notation, if you talk about the sinusoidal, generally one of the harmonics we say, if this is the sinusoidal voltage of frequency f, when we talk about harmonics, if we say what are the basic problems with the harmonics, this is the fundamental component of frequency f. Now if I say third order harmonic is there in a network, so what will be the third order harmonic if the frequency is f? What is the frequency of third order harmonic? 3 times of the frequency. So we call the frequency will be 3f. Of course, magnitude will be less because the magnitude is always divided by 3 by n. If n is the harmonic number, the voltage of the n harmonic will decrease divided by n times. So what happens? Typically, it's not exactly. Typically, if you try to draw a third order harmonic created in this fundamental component, your third order harmonic will be 3 times frequency means like this. So this frequent voltage is typically V by n and this frequency is 3f. And now you add this component with this one. If you add this voltage component with this fundamental component, your voltage will be this will be the shape of the voltage. That means when you find out a fundamental component of F1 like this, and if the frequency of the F3 is like this, the resultant of F1 plus F2 will result to be like this. It is quite something interesting. Here, when you see the shape of the waveforms, you will understand better. Now let us have a fifth order harmonic. So what happens? It oscillates with frequency of 5f. So almost I think you get 10 cycles like this. 10 cycles you can say 1, 2, 3, 4, 5. Yeah. 5. If you tell frequency will be this one. Now if you add this is having a frequency of this is F5. What is the voltage? It is V by 5 and the frequency is 5f. Now if you add this one and this one both with your fundamental, what happens to your voltage? The voltage will be like that. What I want to remove from this concept is whenever, whether it is power electronics or distribution system or power system, whatsoever it is, when you find a voltage shape other than sinusoidal, it means along with the fundamental component of the voltage, that means along with your sinusoidal voltage, there is some other components mixing with this fundamental component which is making your actual voltage to see like this. Now tell me, in the earlier figures, when we find out the voltage of like this, now what does this voltage have? All the parameters, fundamental component f of sinusoidal like that, and a voltage component of it is single phase, triplet harmonic exists, even in power systems are well known about triplet harmonics exist in the single phase. So you have the 3 phase, 3, third order, you have 5th order harmonic, 7th order, 9th order. When you keep on adding these harmonic elements to the fundamental component, the same shape will finally remain to be experienced. So when you are generating a wave, so it doesn't mean just you are generating such waveform. That means when you are operating this inverter, and when you see observing such voltage across this load, it means fundamental component, all triple harmonics along with order of harmonics are being flowing between your DC component and your load. That means all such components are flowing through your load, where physically you see the voltage shape of the same. Now, when you talk this, when we talk about this output voltage, now what happens when the shape of the voltage, output voltage, is changing from square wave to a 3-step voltage waveform? It means some of the harmonics are absent. Typically, in the case of 2-level, 3-phase inverter, the shape of the voltage is better. Little bit side. Why so? Because the triplet harmonics, that means whenever you are going for a single phase inverter, you have the harmonics of third order, that means 3, 5, 7. Even order harmonics cancel each other. They are never available. So 3, 5, 7, 9, 11, 30, everything are added up. In case of 3 phase, what happens? The third order harmonics cancel each other because they are 3 phase nature. So what happens? Out of 3, 5, 7, 9, third order, 9th order, 15th, they get cancelled each other. So as the harmonic content in the 3 phase is reduced, instead of square wave, the voltage appears like this. Little bit compared to that. Now coming to this case, it is much more sinusoidal because now you are extending your inverter from 6 pulse to 12 pulse, and using the transformer you would achieve such voltage. It is much more sinusoidal. So what happens when the pulse number is enhanced? The harmonic number less than the pulse number will automatically cancel. Like now you are going to go for 12 pulse inverter, the harmonics which are lesser than 12 pulse will automatically nullify, and that's the reason your shape of the voltage remains much more sinusoidal. Now coming to the, so if you want to achieve such target, the phase difference in the transformer should be maintained 360 by its pulse number, which gives the more sinusoidal voltage. So now in case of sinusoidal PWM, what happens is in case of sinusoidal PWM, the sinusoidal PWM, what happens? In this case, what happens? The alignment of the pulses are in such a way that we have the carrier and we have this reference voltages, and when the output voltage is of PWM nature, in this case, the harmonics which is less than FCR, means carrier frequency is nothing but FCR, and the modulation frequency is nothing but your reference voltages is 50. So if the carrier frequency is 1000 and if your modulation frequency is 50, 1050 comes to 20. So all the harmonics which are lower than 20 will cancel and the harmonics above 30 will remain the output voltage. So that makes your output voltage to be equivalent in nature by removing the harmonics from the inverter output voltage. Now you understand that when you go for PWM technique for an inverter, as you increase the carrier frequency, so the FCR by FM, the number increases from 20 to 40 or 40 to 60 and so on. The harmonics which are lesser than this modulation index will reduce, will be cancelled. So what happens? The voltage nature will improve. Keep this point in the mind. Now, coming to the multi-rail inverters. Why basically we go for multi-rail inverters? We have discussed about the two railway inverters which are